Right. Proposition 11 says we can, if we're given a straight line and some point on that straight line, we can construct a perpendicular to the straight line that passes through that point. So in other words, if you're given the straight line AB and you choose just any point you like on there, point C, we want to be able to construct a perpendicular line, a line that is perpendicular to AB and passes through the point C. So let's do that. How do we do it? So first one, choose any point D. Let D be some point specifically on AC. So to the left of C in this case. We'll choose, let's see here, just to make the diagram a little more interesting, I'll choose it kind of further out. I'm pretty sure that I'll have to extend my line AB, or at least kind of extend it over a little bit more, but that's fine. That doesn't really change anything. That doesn't violate anything that we're trying to prove. So let D just be any arbitrary point that is on AC. We're going to construct CE. So we're going to find the point E, CE, such that CE is equal to CD, right? And this is proposition 3. But as far as actually doing the construction, it's just a circle. Because it's a circle with center C and radius CD. So where does that fall? Oh my goodness. It falls exactly. Oh, that was super unintentional. Oh, that's crazy. I was really trying to not do that. It literally falls exactly where B is. What are the chances? Whatever. It doesn't matter. It doesn't matter. All right. CE, also CB, apparently. That's totally happenstance. You can do this on your own, and you can do it so that E is not going to coincide with B. That's just absolutely coincidence that happened. Why does it look so fuzzy? Everything looks so fuzzy today. I don't know why I keep focusing this thing. Probably I need to get a better everything, better lighting, better camera. Right. So prop 3, we've made CE equal to CD. Next, on DE, we want to construct an equilateral triangle. So we're going to construct equilateral triangle, and we're going to call it DEF. So an equilateral triangle with side length DE. Let's do that. Right here, boom. Let's see, and I suppose I'll actually make the triangle, since it's just to try to make the diagram as complete as possible, because really all that I need is this vertex. You probably already see it already. I just need this vertex of the triangle, which I'm going to call F. If you join FC, that's the line that we're looking for, but I'll make the triangle anyways because it'll be helpful in visualizing the proof. So construct equilateral, and again, that's proposition 1. It allows us to do that. Join FC. And how can we join FC? Well, you already know it by now. It's postulate 1. Last time I said proposition 1, and I meant postulate 1. I think I corrected myself in that video, but postulate, proposition. Why do the words have to be so similar? They mean different things. What the heck? All right. And so claim is that FC, again in kind of modern notation, is perpendicular to AB, and then obviously because FC contains the point C, it passes through C, which is, also what we wanted. We weren't just trying to make any old perpendicular to AB. We wanted a perpendicular to AB that passes through point C. I've got like other papers under here. They keep kind of shuffling out. Right, okay. Well, if we claim that, we got to prove it. So, how do we prove it? Okie dokie. Well, we know that DC is equal to CE. This is by construction. We made it that way. DC equals CE. And CF is common. So whenever we say that CF is common, you can bet that we're going to be looking at two different triangles, and like just kind of thinking ahead, probably where we're going is that we're going to prove that these, in some way, maybe these triangles are congruent. That's just my guess. Let's see where Euclid takes things. He's much more clever than I am. So CF is common. The two sides DCCF are equal to the two sides ECCF, and then the base DF is equal to FE. So then DF, that's a DF equals FE, and again, that's by construction, because it's sides of an equilateral triangle. So DF equals FE, which means then, by proposition 8, it must be the case that angle DCF equals angle BCF, or he says, I suppose, ECF. Right, yeah, ECF, which would be the same thing as BCF. All right, by proposition 8, DCF equals ECF. So side, side, side gives us that these two angles right here are the same. And in order to finish this thing off, we have to kind of invoke one more definition, which is the this is the first time that this definition is coming up in the elements, aside from like in the list of definitions. This is definition 10, which is the definition of a right angle. And let me just read what is stated. It says, but when a straight line set up on a straight line makes the adjacent angles equal to one another, each of the equal angles is right. So when we have this straight line, FC, set up on another straight line, AB, in such a way that the adjacent angles that are formed, if they're equal, these angles are the same thing, that means that the angles are right. And that's what we just found. So by definition 10, it follows that angle DCF and angle ECF are right angles, which is what we wanted. Right. That's exactly what we needed. This one get a QEF? Yep, sure does. So there it is, to draw a straight line at right angles to a given straight line from or through a given point on that straight line.